Fabric-reinforced soft robots, like Squishy, shown here, consist of one or more elastomer chambers that can stretch when inflated. Fabric is placed within the elastomer matrix. The chamber will not stretch at this location, allowing the kinematics desired to be designed in. These robots are in need of a dynamic model to predict and control their motion. Models from continuum robots designed around a longitudinal steel spine are often used, but should they be? With heavy payloads and lower chamber pressures, the walls of the chamber can kink or buckle. These areas of high localized deformation pose difficulties for models that make the assumption of continuous curvature. We take a different approach. Instead of treating the chamber as a flexible spine, we treat it as a series of discs, each connected to the next by a single inextensible taut thread. The constraint of the thread represents the behavior of the fabric reinforcement. Since the thread does not have any bending resistance, the kinked configuration shown here is easy to represent. We used Wolfram Mathematica's replace operator to generate analytical expressions for the equations of motion for a collection of disks. The iterative structure of the partial derivatives of the angular velocity with respect to the DiscThread generalized coordinates and their rates of change made this possible without explicitly taking symbolic derivatives. While these expressions can get long, they can easily be saved to the hard drive even for large numbers of disks. We constructed an environment in Python which parses these expressions and numerically integrates them to solve the initial value problem. In the 4-disk animation shown here, we can see the robot fall under gravity until the gravitational moment arms on the disks become small enough for the effective chamber pressure to make it curl up.